Well, we're just about there. Welcome back, folks. I hope you all had a great spring break. For me, it was fighting with procrastination mostly, but I hope it was more productive for you all. We're in a pretty interesting place in the course, and usually for this semester, spring break is more disruptive than you would think. Because what happens on spring break is we all had a pretty specific routine of getting through classwork, coming to class, all that kind of stuff. That routine died for a whole entire week. And we come back with a lot of serious work still on the table. This doesn't happen in fall semester. You only have like a couple weeks after Thanksgiving break. We've got week 11, we're doing sequences and series. Week 12, week 13 will be similar. Week 14, we'll go into our third exam. Week 15 is a review week, so that'll be nice. Week 16 is already finals week. So us being on week 11 means there's a lot of stuff going on, and we're coming to the end pretty quickly. Here's where we are if we're looking in the syllabus. We should be completely done with section chapter 11, do some work in chapter 10 before we're in exam 3. So whatever section we end up right here, 100% complete, will inform what makes up exam 3. Then we do a couple more days. And like before, if we decide to have a review day right here, that would be appropriate. So we'll do exactly what we did ahead of exam 2 when it was over here. We'll have our entire review week right here for closed week, and then we'll go right into a finals week right after. Our final is May 5th, the worst time ever. This time doesn't work for you. I do make adjustments on that. I usually give an earlier exam as well. But that's what the plan is so far. Currently, we're in section 11.3 on the last portions. But any questions or comments at the moment, folks, before we get started? Okay, I guess my spiel from coming back from spring break is it's rough because we had to stop and start again, and that's not easy on anybody. And we have a lot of work to get through. So these last weeks are the most pivotal week for the class because looking on this end of the syllabus, we have a final exam and one exam still left on the table. That's 40% of the entire course. There's plenty of time to improve your grade, things like that. Again, it's very pivotal on the last set of weeks, right after spring break. Kind of unfortunate, but I hope it was a great break. We'll get through some intense work, and then there's light at the end of the tunnel coming up really fast. Before we get too far in our new material, here's where we left off on before going into spring break. We were dealing with the integral test. If you use the integral test on this series right here, where the value of p is allowed to change, you find that it's going to be convergent exactly when p is bigger than 1, divergent when p is equal to less than or equals to 1, and it's the harmonic series when p is exactly 1. We said right before we went on to break that this is like the best test ever, though. For what we've seen so far, it's the easiest one to apply. Right here, we see that n is a base, and it's in the denominator, so it's automatically a p series. We found the powers exceeding 1, so it automatically converges. This one was a trick because watch out where your base n is. It's got to be in the denominator. It revealed the correct power we're dealing with. It's actually greater than 1, positive 5/3. So by Pierce series test, it converges again. And this is like a worst case one, not really appropriate for an exam, but it is appropriate as a homework problem. The base is n. That's what makes it a p series. We have base n denominator and numerator. So when we consolidate down into the denominator, we get pi minus e, which is less than or equal to 1. So we said that that one diverged in this case. And that's all there is to say about p series. And that's what makes this document right here, be hyper familiar with this document, really the major way to maneuver through chapter 11. You can do for every single p series that ever comes up on every homework question, every exam question, the whole integral test, but I promise you, you're just leaving a lot of time on the table. It's these tests, it's more about find out what fits it best, which one can maneuver through the process the fastest. Sometimes that is the best test, but it's really not very often. On an exam setting, it's usually just one question that's going to line up with the integral test. And I would give a hint on that one. Use the integral test on this problem to give you an idea that for the rest of them, it's going to be one of these. And part of our job is to determine which is the right one. That's the next thing that's kind of hard about this. We'll be practicing that all along. These questions down below, if we were like really behind on material, could be problems on exam 3. We're going to go beyond this on exam 3, but this is what it's all about. This is the test that we have so far. It's all mixed at the moment. And in example 3, you have to determine just what fits these and then execute the test. So first on part D, anyone see what fits it best? Is this test for divergence, P-series, or geometric series? I agree with you, good call. The thing that stands out to me that really makes it geometric is the fact that n is not a base, it's an exponent. That's what the geometric series is all about. So up here, n is as an exponent fitting in. We just have to get to this structure right here. A power r, show it's less than 1, that'd be convergence, or show it's greater than or equal to 1 for divergence. The way this example 3 is written as well is pretty much what you're going to see on the exam. We have to say with the final conclusion if it converges or diverges. We also have to say the name of the test we're about to use. The one we said that this was the geoseries, we could have just said geoseries test, or just geoseries would have fit the bill there. We have to show all steps of that chosen test. And all we're doing is determining convergence or divergence. So convergence happens here, divergence happens right here, greater than or equal to 1. Let's next say that this is equal to an is the 3n divided by 5 power n minus 2. I want to write it as a common power r to the power n minus 1 and see what else pops out. That a there might be revealed. One thing we can do is, this needs to be a power n minus 1. So to make it go up a power, you can visualize that by going times 5 over 5. So now over here, that will go up by 1 power. This one has to go down by a power, so you can factor out a 3. And now it's 3 power n minus 1. So we're handling two things at once, just to target the n minus 1 as an exponent. And the numerator, we have 5 by 3 for a 15, times the fraction, 3 power n minus 1. At the denominator, we can combine the bases and get 5 power n minus 1. And then this results in 3/5 power n minus 1. That's the major thing we had to do to come up with convergence or divergence. So looks like we're in this outcome right here. All we now need to say is those last bits of conclusions. This is us showing all the steps. We're algebraically manipulating the nth term, getting into this structure, so we can say r, in absolute value, is 3/5, which is less than 1, so it converges. And this is a weird problem. We're kind of done at this step. Those instructions just said determine convergence or divergence. When we were in section 11.2, there's additional instructions of saying if it converges, say what it converges to. I couldn't say that on this problem because if I said it, I would have immediately revealed this one was the geometric series, and these ones, I can't tell you what this converges to at all. That's a much harder problem. It's only the geometric series we can do that summation. So if the geoseries is mixed up with all the other series, we usually just end right here, determine the convergence or divergence of it, which feels unsatisfactory. So if you want to practice an additional step, here's what it would look like. I'm going to show it in ordinals just to convey our work is done right here. But summation an is now summation from 1 to infinity of Instead of putting in this AN, we'll jump way over here. 15 times 3/5 power n minus 1. Then from up here, let's see, here's the formula. It's kind of not formatted the best. That should help out a little bit. Using this part of the formula right here, we can say that this is equal to 15. That's the A value in the numerator. Over 1 minus the R value is 3/5. So that's the exact quantity it will converge to. And then simplifying is just multiply by 5/5. We get 75, 5 minus 3. So it converges to 75 halves exactly. Let me try that numerator again. So this is the problem that we did in section 11.2, when it was mainly just the geometric series and test for a divergence for another block of problems. Here, if this was a real exam question, feel free to end the problem right here. These instructions or these steps right here is if the problem asks us to compute the sum. Also keep in mind, you can only compute the sum if it actually converges in the first place. What we're saying is, as n gets bigger and bigger, and you're adding together more and more terms, heading towards infinitely many of them, those terms in their sum total are getting closer and closer to 75 halves. Well, any questions at all, folks, with our first one there? Okay, so we've got test for a divergence, geometric series, P series, and integral test. That's our whole landscape so far for sequences and series. This is our next review problem. But notice it kind of is not nice in a way. It's automatically not a P series. Even though a P series has n as a base, this one's not a P series because n appears in a couple locations. If it looked like this instead, then, well, that one is more similar to a P series because now you can divide, go 7/5n minus 2. Well, this part is a P series, that part's not. But if it's this way, we can't divide and separate. 2 terms in the denominator means we're just essentially stuck on this one. So the P series is out. If n is as a base anywhere, it's automatically not a geometric series. That leaves either the integral test or test for divergence. Anyone see the optimal way to go? Good call. It's really on the top of the notes only because it's the first one to think about every time you eyeball a new series. Ask yourself, what would be the limit of that term highlighted in red? That would be -1/2. That means the test for divergence is automatically done. And now notice, you could have used the integral test, but you are working like 10 times as hard in terms of the amount of time it takes to run through that whole test. So for test for divergence, here's what the steps look like. You have to state the name of the test. So let's just say it either here or at the end, you could say diverges by test for divergence. Usually it's a good idea to just call your shot right away so you don't forget. Test for divergence. If you like to shorten things up, test for div is a great way to shorten it. Or sometimes this is called nth term test. It is a totally synonymous way to say this test. All we do is we take the limit as n goes to infinity of an. An is referring to the nth term of this series right here. So it's limit as n goes to infinity, 5/n, 7 minus 10/n. We go back to that thought of any limit heading towards infinity is picking up a horizontal asymptote. On this one, the horizontal asymptote is the combination 5 divided by -10, only because the powers of n above and below are tied, degree 1. So we get -5/10 or -1/2, but honestly, I don't know if you needed to simplify it. Either way you look at it, it's not equal to 0. That's this part of the steps. All we need is a conclusion, so we can say, therefore, summation an diverges. Then our work is totally done right at that step. Any last questions, folks, on test for divergence? It's a nice test in a way, right? Really the best test that we want to try to hit anytime we're looking for a series and we're trying to categorize it is we're hoping to test for a divergence, geometric series, or a p-series. Those are the majors ones that go really, really fast when we recognize them. Then integral test and the comparison test are where it gets a little bit more technical. Here, let's see, is there anything left to say? Not really, but you might have not liked that shorthand too much, where we said summation an. We use it again over here where we took the limit as n goes to infinity of an. All it was referring to was that bit right there, the nth term of the series. I think we've got another one. Here's the last one for these notes, part F. Now, part F has a lot going on, right? It's arctangent or tangent inverse in the numerator, divide by n squared plus 1. First thing you'd want to do when you're thinking about this one is, what happens in the limit of tangent inverse n? Anyone happen to recall that limit there? Good call, exactly. The limit of that one is pi over 2. How does that help us? Well, it tells us the test for divergence is out. It's off the table. If we tried it, we'd take the limit as n goes to infinity of tangent inverse n divided by n squared plus 1. But here's the graph of tangent inverse n, just to get another view of that limit. Horizontal asymptote, pi over 2. Another one not as relevant at negative pi over 2. Arctangent goes like this. So in the numerator of this structure, it's getting closer and closer to pi over 2. It's bounded, in other words. It doesn't grow beyond pi over 2. It'll never hit 2. Yet the denominator is a degree 2 quadratic. It grows to infinity without bound. The whole thing is getting closer and closer to 0. And the limit, it's exactly 0. And that's unfortunate. The moment you get limit exactly 0, it means test for divergence fails, in the sense that it cannot give us any information. It can't even be used in the first place because the limit did exist and the limit is 0. We don't meet the hypotheses whatsoever. And so the conclusion is off the table. In fact, this one looks like it converges actually rather than diverges, because we have something like a 1 in the numerator and something like an n squared in the denominator. It's so much like a p-series that we just can't analyze it that way, because the second n is in a function, it's not exactly a p-series any longer. It means we have to use the integral test on this one. There's no getting around it. But as you think about how hard we're working on this one, even though the conclusion might seem obvious to you, that's what the next section is all about, the comparison tests. This one is actually very similar to 1 over n squared, which is a convergent p-series. We can find a systematic way to compare it to something we know that converges. One of these three right here, tests being used, in other words, that's a smarter way to do this problem. So we're in fact doing it the hard way because that's the only tool we have, the integral test. So let's grab this one and give this test another try. The idea with the test is, if we call this summation an using that shorthand, it allows us to define a new function. Let f of x be equal to, and here's how it's defined. Let's see. That way, we just take the nth term and define it as f of n. But we also define it as f of x at the same time. So we'll write it as tangent inverse x divided by x squared, not n squared, plus 1. Once we define it this way, then it has this property down below. Plug in an n, and we get the nth term of this series up here. So we have a function. We need to give it a domain. Let's say, because it starts at 1 here, it's defined on 1 to infinity. So we always match up this part right here. Next thing we need to do, this is for our own knowledge to see if we're using this test correctly. Take a look at the hypotheses. This one is continuous on the entire real number line because it's a ratio of continuous functions and the denominator cannot be 0. So we can automatically say, then f is continuous. Positivity, now that depends. We're looking into this next condition, positive right here. Well, because the domain starts at 1, we're on this part of the function. We do have positivity on the correct domain. If it was the entire real number line, it would match up with the integral test, but then this part would have been lost because tangent inverse does turn negative. We can say f is greater than 0 on our chosen domain from 1 to infinity. And next, it has to be a decreasing function. Well, absolutely is. Even though the numerator increases a little bit, the denominator increases gigantically without bound. So we can say, since n squared plus 1 diverges to infinity as n diverges to infinity, and tangent inverse of n is less than or equal to pi over 2, we've got a bound on the numerator, denominator grows without bound. This is just a really long way to say f is decreasing on 1 to infinity. So 3 hypotheses we have to check, which means the integral test has 3 ways it could go wrong. If any one of those hypotheses break, then we can't use the test whatsoever. One thing to keep in mind, though, is sometimes these functions aren't really increasing or decreasing on that whole domain. Maybe for a while, f actually increases. But if there's a number, maybe 12, where from 12 to infinity, it eventually does decrease, that's good enough. Because what happens then is, imagine just throwing away finitely many terms on this series right here, run the test on the rest of the terms, that part would converge. Then the convergence divergence of the whole thing is never influenced by finitely many terms. So if it's eventually decreasing for all time, you're good on that hypothesis as well. However, if it feels like you're doing more algebra and calculus just to resolve decreasing, you're probably working a little too hard. So if you're breaking out the first derivative test for increasing, decreasing, solving for integers n for when it's eventually decreasing, it doesn't have to be that hard for these kind of problems. But here's the next exciting thing we do. We have to do an improper integral from 1 to infinity. If that integral converges, so does the series. If the integral diverges, again, so will the series. Their fates are now tied to this thing. Integrate from 1 to infinity, f of x dx. We have to show this one step in the setup where it goes limit t goes to infinity, integrate from 1 to t. Let me also drop in f of x, tangent inverse x, over x squared plus 1 dx. So don't forget to show this setup step right here. Finally, integrating this one is not too bad. If you let u be tangent inverse, its differential will involve x squared plus 1 immediately. So we can start off by just saying set u to tangent inverse x. Then differential du is 1 over 1 plus x squared dx. And that's a pretty fast substitution. This whole part is du. The numerator itself is going to turn into u. Except you also have this other thing that you have to make a decision on. Either leave the limits of integration as they are, or change the limits. Let's continue with the same process that we've been using all class along. X equals t, x equals 1, implies u equals tangent inverse t, u equals tangent inverse 1, Tangent inverse 1 is exactly pi over 4, so we have a nice value on the lower bound. A more abstract value on the upper bound, but notice we also have a graph that's going to help us out with that limit as well. That's just a t right there. Let me fix that. So using that substitution, we are now back over here. It's the limit where t goes off to infinity, and lower limit is pi over 4 now. Upper limit, tangent inverse of t. This whole thing, tangent inverse of t, we wrote in as u. It's kind of a nice antiderivative we're gunning for now. Dx divided by x squared plus 1 is du, which means the integration part of this, well, the antiderivative part of this is not the bad part. It's more defining the function, checking the hypotheses, and navigating the improper integral setup steps. But here's where we're going to land on. We'll take a limit as t goes to infinity. Antiderivative on this gives us u squared. We divide by 2, so here's 1/2 in front of the limit to counteract that part. U squared is evaluated from pi over 4 to tangent inverse of t. So now it's 1/2 times the limit. T goes to infinity. And now we're just evaluating. So first it's tangent inverse t squared minus pi over 4 squared. And we still have to take the limit of this part right here by the red dot, but supported by this graph. As t goes off to infinity, we're just getting closer and closer to pi over 2. So we drop down over here just to pi over 2 squared. That's really the last step we have to take with the limit, because once we write in, this is 1/2 pi over 2 squared minus pi over 4 squared. Another problem is we might have simplified that to say what the integral is converging to exactly in a simplified form. But that's not the point to this problem. The point to this problem is the series right above. Down below, we have a finite number. You can just say the integral converges. Then, by the integral test up above, we can say this original series, summation an, must converge as well. Let's say that down below. Therefore, summation an, referring to the original series of the problem, must converge. And if this was a real exam question, maybe it's 10 points as an exam problem. Homework problem, maybe 5 points. In either case, we could lose 1 point on here because there's still one small detail missing. Anyone see what's missing out of all this? Exactly. We never said what the test was. It's a small thing. But really, each time you do this, if you write down, I'm using the test for divergence, I'm using the geometric series test, it seems small, but that's working its way into your head for the purpose of just trying to tell apart all of these strategies right here, separate them in your mind, so we'll know when to use them. So it is a required step we have to say on each one of these problems. All we need to say is, by the integral test. I don't care how much you shorten these up. You might have said int dot and t dot. That would have been fine for integral test. Anything that just conveys to me that you know that it was this test you're using specifically will get that last bit of credit. Well, that's the conclusion of the integral test. One nice thing about the integral test is that it gave us the p-series test. That's one great takeaway. Another big takeaway in part F is this is like the hardest way ever to do this problem. If we had the comparison tests, one or the other, there's 2 of them, we could have done this in a smart way in like a quarter of the time. So that's what we're going for next, the so-called comparison tests. Any questions at the moment, folks, before we take a look at those next new strategies? Okay, just making sure this actually saves. And here we go. We're now in section 11.4. So far, I think sequences and series, they don't seem too bad to most people. It's a lot of stuff. It's a new way of thinking. It's right in 11.4 where things start to pick up a little bit more. We're picking up two additional tests, the comparison test, the limit comparison test. But the feature about both of these tests is how they interact with everything above and below. The integral test, or excuse me, the comparison test and the limit comparison test very often use these as well in the background. So when we go to use either one of those tests down below, we're often using one of these to support half of the conclusion contained within these two. So it gets a little bit more dicey on this part of the course, but like the other sections, we'll go slowly and carefully. Let me know if you feel like a different way of looking into these kind of problems could be helpful, because some of these problems could be done in a number of different strategies. It doesn't always have to be a comparison test. Maybe you see a problem like this and you decide, I want to use limit comparison test. Totally appropriate to try a different strategy. It's kind of rough to have two tests with a very similar name, and the actual process that we use the test is totally different. This is a harder test because you have to make estimates. We have to show our work in those estimates. They have to be justified. It's this step right here by the red dot that makes the ordinary comparison test a little bit dicey. Let's take a look at how it goes. It says, if the series, well, hang on, the major thing that's confusing about this is we're comparing two sequences simultaneously. Then you go to compare two series simultaneously, all at the same time, and they're contained through the estimate to give you a conclusion. There's really a lot going on in this problem. So it tells us the question is about summation AN. So I'm often writing down this as a shorthand. We started doing that in the last sections really because we're coming to this point where we handle two things that simultaneously. A variable name is worth a lot. So when it says we're considering the sequence and we have conditions about AN, the series we're considered on the right-hand side, means BN is a whole new series that we have to come up with. And if we look at the terms of the sequence, it must have positive terms as well. Pretty restrictive situation to always say positive terms, but next test is going to be the alternating series test, which will have handle the opposite signs. So we give the given series a name. Its role is always AN. That's important because AN is always the conclusion in the comparison test. So let's box that out just for emphasis. We come up with a new series Bn, and, well, the new series Bn that you come up with is where you're looking at this and deciding to yourself, this is related to something very similar to, compared to summation. The index of the summation should be the same. This one's starting at 4, so we don't divide by 0 on one of its terms. So we'll start at 4 here as well. Go off to infinity. And if instead of 1 over n minus 3, that's not a good series because it's not a p-series, it's not a geometric series, test for divergence fails, let's exchange it for where things are a little bit better. Anyone see a good change to make right over here to simplify it? It's weird because by simplify it, I don't mean algebraically simplify it. I mean, delete the part of this term of the series that you don't want to deal with. It's the -3 part, right? If it looks like this, your work is done. It's the harmonic series, diverge, known to diverge. Or you could say, apply the p-series test. The power p is 1, it's known to diverge. The fact that it had n minus 3 here is what's throwing it all off, right? We want to lose that part completely. So we compare it to something with that part just completely eliminated. But notice you had to come up with that on your own. That's what makes the comparison test in part a little bit harder. And this isn't even good enough. Once we come up with the right thing that we decide to compare it to, we have to run a test on that as well. You could use the p-series test, but this is one where it has a known name. We could just say for this one, this is the p-series, harmonic series. P-series as a test would work. P is 1, which is divergence. But let's just give it the name. This is a harmonic series. Known to diverge. So when it says give a conclusion of convergence divergence, for all series tested, notice this got pluralized this time. It's because you're doing multiple tests every time a comparison test comes up. It's now more than one. But if it's a named series, you can just cite that name and what it does. Harmonic series diverges. Now we're on to part B. We've eliminated this entire possibility. The series we converge or comparing to is a divergent one. So this now informs us that's your next step. And we really have to show that step. We have to show the estimate AN is greater than or equal to BN. This doesn't always work out. Sometimes, for example, if that was an N plus 3, I would still compare it to 1 over N, but that estimate is never going to work. We need a limit comparison test. So if that ever happens to you, if you're trying to make this estimate work out, but it's algebraically not feasible, divert to limit comparison test. Let's say here, we're using, let me say it this way, using the comparison test, we must show AN greater than or equal to BN. And that's only because we said diverge there. If we said converges, we would have been doing the opposite inequality, AN less than or equal to BN. We'll see that one in the next problems. So we must show this for credit. And here's how it goes. I want to focus on the denominators. This one was called AN, and let me do a little bit better on labeling this one. Giving these actual honest names is worth a lot, but I'm not sure if that's going to fit in too well. Let me do it this way. This is summation Bn. I'll just try to remember better to give it a name as we define it. So we know what the An and the Bn is in this problem. Once we get that estimate to go in that direction, then the thought is, if this holds for all n greater than or equal to some starting value, n naught, or for all n, if that happens to be the case, then An is bigger on every one of its terms in the sequence than this sequence, which is related to a series known to diverge. An is bigger than a divergent series, it must diverge as well, is the thought process behind it. So here's how we'll start. Look into the denominators first for this kind of problem. I want to compare n minus 3 on the left to n on the right. Now the inequality going this way is going to be less than, strict less than inequality sign. We're trying to make it go the other way, but that's all right because algebraically, when you now take the reciprocal of both sides, it implies an inequality changes in this direction. We'll have 1 over n minus 3 is now bigger than 1 over n. And that's the effect of taking reciprocals of both sides. Inequality flips directions. Does that make sense to folks so far on that statement? Awesome. But then that means we're done. Left-hand side is an, 1 over n minus 3. Right-hand side is bn, 1 over n. We showed the estimate, an is greater than or equal to bn, and this works for all n. Let's say that here just for emphasis. for all n. Finally, our work is done. If the terms of the series an are always larger than the terms of the series bn, where bn diverges, we get to say this. Therefore, summation an must also diverge. We already said we're using the comparison test, so we don't need to restate that. You're never forced into being redundant in that kind of way. But this is how the direct comparison test, or just calling it the comparison test is fine, goes. This is kind of a warm-up problem. It can get a good bit nastier, so that's our goal. Practice the nastier ones as well. Actually, let me leave that highlighting there. Any questions at all, folks, on this one before we try another? Okay, so here's our next one to try. Maybe one last thought, because these tests, again, are really touchy. The comparison test itself is very touchy. If I had that was n plus 3, it still diverges, but that would be a greater than sign. And when we go to take the in reciprocals of both sides, it becomes a less than sign, mismatching. We want greater than or equals to. So even if it's a plus 3, the whole test is off the table. It's pretty frustrating. So that's why we have a secondary test for that outcome. The limit comparison test will handle that whenever it comes up. If you're worried about that kind of thing happening in the homework problem, I mean, it's awful to try to force something to estimate, right? When it's impossible. On the homework assignment itself, I put down some guidance. Direct comparison test, the one we're using right now, works well on these exercises. Limit comparison test is the only thing I would use on those exercises. You might get a direct comparison test to work, but in my opinion, it's not even worth it. Go for limit comparison. It's the more powerful technique. And those are nastier problems to work on. But because we're learning this, we'll try it out all over again from scratch. Here's a harder scenario where there's stuff in both the numerator and denominator. So what was provided was the series an. Now we want to compare to a new series. Let me call it bn to start. And again, this looks really small, but if you have conclusions on two different series and two different kinds of conclusions, naming things is a really, really good idea. It separates them in your mind, allows you to navigate through this theorem in a more clean way, just seeing where each part actually fits. So how do we get bn? We do the same kind of cheesy thing we did before. We just delete the parts we don't want. Sounds strange, but here's another way to think about it. Let's pop out this thing because we're going to need it shortly. This series right here is so close to being a p series. If it didn't have the -1 and it was just an n in the denominator, if it didn't have the +1 and it was just n cubed in the denominator, it would have turned into 1 over n squared. You can analyze it as a p series automatically. That's the motivation about the comparison test. It's as if we took something nice like the p series, just moved around some constants in an annoying way, and now it's no longer a p series, but it has every right to converge in the same way a p series does. So the numerator, we just grab n. That's the important part right there. And the denominator, the other important part, let me use some kind of highlighting here to convey, just n cubed, so that's all we grab for the denominator. Then let's simplify it. It's now a series from 1 to infinity of 1 over n squared. We have to test even this series right here. So we'll say that this is a p series. We have to show all steps of the test, but the steps of the test are this. P equals 2, which is greater than 1. We have to give a conclusion for every series that occurs, but for the p series test, we have convergence if p is greater than 1. What I'll always write down on paper is this condition, greater than 1, is the condition upon which convergence happens. I strongly encourage you to do the same thing on paper every time, because that's how you start to memorize these tests. It becomes muscle memory the more you do that. That's the condition on convergence. So we'll say from here, converges. Well, the moment we did that, we're comparing it to something that's known to converge. It means that part is totally off the table now. We go to the first line of the comparison test. Bn is known to converge. It's a p-series. We now need to show this estimate as our next step. Using the comparison test, we must show An is now less than or equals to Bn. It's the opposite estimate. But what we're saying here is that if Bn converges to some known value, and if you can show that all the terms here are always smaller than Bn's terms, An's got to converge as well. It's even smaller than this total sum of Bn over here. So that's the logic of the comparison test. But the actual estimate we have to show is not always easy. So here's how it might go on this one. Let's focus on maybe the denominators like before. Usually that's a good place to start. We can say n cubed plus 1 is certainly strictly greater than n cubed. So I grabbed that denominator, I compared it against this one. We're forced into that inequality sign, greater than. This would then imply 1 over n cubed plus 1, flipped inequality because we're taking the reciprocal of both sides of this inequality statement, is less than 1 over n cubed. It's not quite there because we have to work on the n minus 1 portion, but it's close. So I need to put something here that's smaller than something I put in this numerator. We can say, since n minus 1 is in fact smaller than n, we can put those into those numerators and it doesn't change the inequality. Or think of it in this term, you're just taking this, multiplying the left-hand side by 1 over n cubed plus 1, so it appears over here. But when you go to the right-hand side, you're multiplying by something even bigger, 1 over n cubed, so it becomes n over n cubed, and it supports the greater than direction here from the right-hand side. So since this goes less than, we can now say that part implies n minus 1 over n cubed plus 1 is indeed less than n over n cubed. But that's really good for us because n over n cubed is equal to 1 over n squared, which is the nth term of the series for B. This one is exactly the nth term for the series for n, for A rather, A sub n. So we have what we wanted. An less than or equals to Bn holds because we showed it's strictly less than, and this holds for all n. So this is the weird mystery estimation work that you have to do in the middle every time you use the comparison test. The actual steps you take completely depend on the form of the original series that was provided and what you're comparing it against. So again, it makes the comparison test honestly a pretty tricky one. Usually, if I see something like that by the red dot, I'm going directly for the limit comparison test. Because anything that I do wrong here that goes wrong, maybe it was an n minus 1 in the numerator, excuse me, an n plus 1 in the numerator, that alone messes up everything right here if it was an n plus 1. But we do have a conclusion. We stated the test, we showed the steps, and now we can say, therefore, summation an, the original series now, must also converge. So that's the comparison test so far. They're pretty tricky, but we should do one more just for the sake of really nailing this concept. We'll take a look at one last one. Any questions or comments first so far, folks? Okay, one more comparison test. And then this feels like it's almost a sell on why the limit comparison test is so powerful. We'll see how to do this one next. After that, the limit comparison test, like I've been hinting at, is a lot nicer. So this section is not as terrible as it really seems. But this one is kind of an interesting one in a certain sense. This part C is just a reminder that every single time you do a comparison test, you also have to do these estimates in the middle. And the way you do those estimates varies wildly from problem to problem. It's really quite strange. But here's the thought on this one. Let's rename this as summation AN. This will be a common strategy of just fixing a symbol like this, like a variable x, in other words, to this entire actual definition of the series. So once we write down that, the new thing about this problem is cosine squared n. It's really kind of weird to throw in there, but we do know a lot about cosine at n. It's less than or equal to positive 1 and greater than or equal to negative 1. That's if it's not squared. So cosine is a bounded function between negative 1 and positive 1. If you square it, you don't change the fact it's bounded, you change the bound itself. So imagine squaring it now. Cosine squared of n will still be less than or equals to 1, but every time it got negative and we squared, it flipped to positive, so now it's greater than or equal to 0 altogether. So cosine squared n now has this feature. Kind of strange. Think about n, it's an integer, which means it could be, say, 0. That's how you would get a 1 for cosine, but it'll never be a pi over 2, so you could even do this. It's strictly bigger than 0, less than or equals to 1. It can't even hit 0 itself because it does it at irrational numbers, and n itself is an integer. So we have a good estimate on what's going on with cosine squared n. We're going to throw in a 1 and call it good because that looks like it's a great estimate for the numerator. Now, what about the rest of it? Aside from eliminating the numerator and putting in a 1, anyone see what other test could be relevant here? Should I stop moving it around? Good call. We're going to put a 1 by the red dot. We're going to delete that 3. We're left with 1 over 7 power n. It's absolutely a geometric series. Looks like it converges too. So that means if we're suspecting convergence, we've eliminated this part of the theorem. It's no longer part of our reality. So we'll compare to summation Bn is a summation from 1 to infinity. Here, we're just giving it a name. To the right, we're defining it. Because of this part right here, we're throwing in a 1. Kind of a nice estimate. We're taking something that looks really abstract and just deleting it, essentially. We're losing the 3 and just putting in 7 power of n. Which we could redefine as a summation from 1 to infinity of 1 over 7 power n. Now, we have to test this one as well. Let's make just a comment here, just as a reminder. We must test all series that occur for convergence, divergence. But usually if you're using the comparison test, the test right here on the one we're comparing to, it's fast because we threw down this form because we were already expecting the geometric series to come up. We have convergence if the common ratio r that goes in that spot is less than 1 strictly. What do we have? 1/7, that's the common ratio r. R in absolute value is 1/7, which is less than 1. So this converges by the geometric series test. But if you just said geometric series, totally fine as well. You're implying the test. So let's leave it off here just to convey that's completely fine. I just need some indication from you somehow, some way, this was the test you were going for when you were using the comparison test. Kind of weird, right? We were using the comparison test, but we're really doing two tests all at once. Now, what do we have to do? We have to show that holds. We must show, let's get the colors going here, AN is less than or equals to BN. So let's take a look at the situation again. AN starts complicated, becomes this. Let's do the strategy of, once again, analyze the denominator first and then put it all together. It's kind of a divide and conquer type of strategy. We take 3 plus 7 power of n, compared to this one, 7 power of n. Right-hand side is strictly bigger because it's, well, 3 bigger, right? This allows us to now take reciprocals of both sides. So 1 over 3 plus 7 power of n is now strictly less than 1 over 7 power of n. And we're almost there because this is now the terms for Bn. We can make this look like the terms for An. Our job is done. So here's our last step. We're using this estimate next on by the red dot. And we can say An equals cosine squared n over 3 plus 7 power of n. By the estimate above, will be less than, and this estimate at the same time, cosine squared n is less than or equals to 1. So that's already one estimate, putting in a 1 above. And then when we take the denominator, 3 plus 7 power of n, and just put in 7 power of n, that's another less than estimate. We'll take this in stages. Here, all I used was the cosine squared estimate. We have a less than from that. I'm estimating on the denominator, losing the plus 3 is making my denominator smaller, so the whole thing gets bigger, is another way to think about that. That means we have Bn on the right, and we have the right kind of inequality in the middle, an even stronger one than this condition. Our inequality is a strict one. That means our work is done. We never said what test we're actually using, so we have to say that at some point. Let's say here, this shows An must converge by the comparison. I'll just say comp for comparison test. I'll just say T for test. But I meant to highlight that, so let's just smack it right there. Well, we did, folks. That's how the comparison test goes. It's a nasty test in a certain sense, but when it works well. Yeah, go ahead.
Do you not need to show it in like the full AR to n-1 form?
Oh, the n equals 1 to infinity?
That's the comparison. You not need to take it all the way down to AR n-1. Those are your findings.
Oh, gotcha. You're meaning using this part right here.
Oh, okay.
Yeah, exactly what he was saying. We'd only do this part if the instructions has to really specifically just say, determine if the geoseries converges or diverges. And I would actually have to say geoseries for that kind of problem. And then I would have to specifically say in the instructions, find what it converges to. That's when, yeah, that formula becomes relevant. But the good news is in the comparison test, all we need is that, let's see here, Bn converges. Once we have that conclusion there, we can now go over to the right-hand side and get that An converges as well. But I like that you mentioned that, because another thing that we would want to do with this is estimate what is its total sum. There is some real number that this is getting closer and closer to as n gets larger and larger. We do know that the summation An is smaller than summation Bn. So if we found the total sum of summation Bn, we have an upper bound on what the total sum is for An as well. So even though we never use the total sum here, it has its purpose for the sake of estimations as well. But other questions at the moment, folks, with the comparison test? Okay, well, congratulations, we got through it. I think this is a hard one to get through the very first day after spring break. And you know what the easier one to get through is? It's the limit comparison test, which really makes you wonder, why does the author do the harder test first. It's because the author of our textbook wants to prove as much things as he can, and it turns out this test is proven from using the original comparison test. So the original comparison test is the harder one, but in terms of proving things, that one's harder to prove. So the author displays it second in the textbook. Let's look into the logic on this one before we just run through it. We have two sequences that we're looking into. Both have positive terms. That means when we look at a series, the terms here have to always be strictly positive. Another limiting condition, but we'll see how to undo that strong limitation right here in the next section, alternating sequences and series. So now when we go to take a look at this right here, we're looking into the ratio of the terms, AN and BN. We're saying it comes out as a constant C, where C has to be positive, should be if these had positive terms, right? That'd be weird if it was negative. And it's also a finite number, so no equals infinity, for example. Has to be like 12 or 1, not 0. So 0 and infinity is bad right here. So if you could get that limit to come up as a positive finite number, here's what happens. The fates of both series AN and the one you're comparing it to, let me match up the color coding, are now tied. And what we mean by that is, if you tested BN and you found out it diverged, so does AN because they both diverge. If you tested BN and found it converged and the limit came out right, you know AN converges as well. So the conclusion for both of them is simultaneous, just like the original comparison test. But you know what? We're better at doing limits than making estimates like this. You'll get better at those if you're getting into elementary analysis and real analysis. Loads of work doing these kinds of limits. But for the moment, we're not as fluent in that. We're more fluent in limits themselves. That's one of the reasons the limit comparison test is just so powerful. Well, we've got about 6 minutes. I don't know if we have enough time to do one straight out. That'd be really rushing through it on the first one. Let me just give you the logic behind it. The idea is if the limit comes out as something finite, then the terms of these sequences are growing at very similar rates. We don't have BN growing really fast, causing this to be 0. We don't have AN growing really fast, causing this to come out to infinity. They're comparable. So in the limit comparison, if you get a finite number C and BN converged, but the terms of AN are comparable in this limit, AN has to also converge. And same idea for divergence. Another fun fact is the order doesn't matter. It could be BN divided by AN, same exact conclusion. That's kind of wild for this thing. But usually we just use it in the direct order that we see it. So when we come back on Wednesday, really is not a lot to do on these problems. These are fast problems like the P-series test. But once we finish these up, we will immediately go into a big review problem. So this is reviewing everything on the table so far. If we don't do these kinds of problems, then this is just going to be a big bag of mysteries. So every section that we get through, we have to compare, take a look at what we did. So if you want, you can take a look at these a little bit earlier. We're just going to say which test should we use. And that will be something we come back on to finish on Wednesday before 11.5. Well, sorry we discussed this one, but we didn't get a chance to quite use it yet. Should have took a closer look at the time. Any last questions or comments at all, folks, before we call it a day? Okay, have a great night, folks. I'll see you all in Wednesday's class. Awesome, thank you.
Last homework, like which test I used, if I could just write it in real quick.
Oh, yeah, absolutely.
I knew what I was doing, but I don't think I really wrote it.
Yeah, no worries at all.